Hi there, guys. Well, we're coming on to the last exercise with matrices here. And this is about now taking matrices and raising them to higher powers and making the calculations of these easier by creating a diagonal matrix, which is comprised of eigen values and another matrix, P in this case, which is comprised of eigenvectors as well. So again, this is quite theoretically complicated, but obviously I'll take you through example 13. And in fact, the process of doing it is not all that difficult. Okay, so the important part here is what I'm trying to build up to is this A is equal to PD, P to the minus 1. Then we have this thing here, A to the N is equal to P, D to the N, P to the minus 1. And just to have a look at it up here as well, we've said A is this general matrix here, which has two distinct eigenvalues, and that in that case, if A is diagonalizable, so if it's got these two eigenvalues, then A can be written in this particular form, which is what we're going to talk about in a second, and P is comprised of our eigenvectors and D is comprised of our eigenvalues. Okay, that's not really going to make a lot of sense just yet, but let's just make that one. Let's just show you this. So I've come up with A here, come up with B, again comprised of our two eigen values for this matrix A, and we've got P here, and in P we've got this x1, if you like. Okay, so that's one of our eigenvectors, and that's made up of x1, y1. I know it's just called x1 as an unknown vector, but it splits up into its two components there, x1 and y1. And then we've got the second of the eigenvectors here as well, which is associated with this eigenvalue. So that's essentially from this, which is where we started with eigenvalues. We said, look, if there's a matrix applied to a particular eigen vector, then that's the same as doing a scalar or an eigenvalue times by that eigenvector. That only exists for situations where we've identified the eigenvector. Okay, now I've done that I've come up with a rule here for x1, but I've also come up with a rule here for x2 as well. Okay, and so to take this a bit further, I'm starting with this. And I'm not going to prove that just yet. I'm just saying, if this is true, let's take this matrix algebra a little further. Now, just to save time, I'm not going to put those lines underneath like I've got above, just to make this a little bit quicker. Okay, so now we're going to get to the rule underneath by just doing a bit of matrix algebra here. And the first thing I'm going to do here is apply AP to the matrix P to the minus 1. Okay, so it's to the inverse matrix of P. We do exactly the same with the other side. We've got P, D, P to the minus 1. And this, at the moment, I'll show you where that comes from in a bit, but I just, again, want to get quickly to the rule. So just go with this one for the moment, and then this line should follow through easily. We're just saying, if we apply this to a matrix, it's the same as applying this to the same matrix. But of course, if you apply P to P to the minus 1, or if you apply P to the minus 1 to P, those two things are going to cancel each other out and give you the identity matrix. So that's going to bring you just to A. This becomes the identity matrix, essentially like timesing by 1 in matrices. And so then we've got P times by D times by P to the minus 1. Okay, now, so that's just the same as this. So now we've got A to the N. So we're thinking about, well, what happens if we now raise A to the power of N? So N would be a largish number here. And we're saying that's the same as doing this N times over. So this is really A times A times A, N times over. So I can now write this as P, D, P to the minus 1, P, D, P to the minus 1. And obviously, I don't know how many times that is, so that's N times over. I've got P, D, P to the minus 1. So there's now N lots of this thing here. Now you can see that in between, I'm always going to get p to the minus 1p, p to the minus 1p, p to the minus 1p, and all of those are going to condense so that we get p, d, 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 so that's going to be n times over d, p to the minus 1, which gives us p, d to the n, p to the minus 1. Okay, so this is an important result because doing a to the power of n, doing that matrix multiplication n times, say n is 100, is a difficult calculation to make. There's a lot of processes required there. And that's going to take a lot of computer power in order to work that out. But in order to do this, this is actually really quick because as long as you can find so you can find your eigenvectors, which is what we did in the previous exercise. And as long as we've got the eigenvalues, which is again what we did in the previous exercise, we can make this diagonal vector. Then doing this to the power of n is just going to be this and this to the power of n. So that's really quick to do. And of course, p is really easy. And then of course, p to the minus 1 is easy because we know how to do an inverse matrix. And in particular, with a 2 by 2 matrix, that's quite straightforward. That's even given in the formula booklet. So, so this becomes a really easy calculation compared to this. So that's where we're heading with this. Now, this was a big kind of if at the start. And in fact, that should really be proved as well. Now, in the exercise which is given here, the investigation, you'll see that they come up with a matrix A, and they say, well, show that here are your two eigenvalues, and we've got the corresponding eigenvectors there as well. So again, that's like what we did last time round. So if you've had practice with that, that's not too difficult now. And then they essentially lead you up to saying, well, can you do A times by P, and then can you do P times by D and show that they're the same? And now they're doing that with a particular example here, of course, and then they're saying, well, explain why this is the same. So this is a good investigation to do. I'm going to do it with these vectors up here to show you that this is right. So essentially, I'm showing you this. This is really the key. This is in two part A and B. That's the key to all of that working out, which I've done here. If this is true, then this is true, then this is good. So we just need to show that this is true. So what I'm going to do is I'm going to take PD, and so I'm going to do here P times by D. So we've got this times by this. So let's think about what that is. That's saying this times by this, which is just going to leave us with this times this. Okay, so that's going to give us our matrix here, which is lambda 1 x1. And then we'll have, again, we'll have this times by, so we're doing P times by D, sorry, again, we're doing this times by this, and then we're going to do this times by this. Sorry, it's a bit more difficult doing it back to front. Okay, so that's going to give us lambda 2 x2. It's essentially this times by this, give us 0 there, these two times together. So that's what we're going to add together there. And then, of course, if we do this times by this, it's just going to pick up on, sorry, put it the wrong way around again, this times by, sorry, this times by this. It's going to give us this place here. You can see that's just going to pick up on these two times together. That's going to be lambda 1 y1, and of course at the end you're going to have lambda 2 x2 there as well. Essentially, that's this times by this to pick up on those two times together. Okay, so that's me doing it P times by D. I probably should have written this followed by this because it was actually quite difficult to do back to front. Okay, so there we go, that's P times by D, and what you'll notice there is that in fact this is just your x1 times by the eigenvector. Here we go, there's the eigenvector. So imagine that that's our eigenvector there, x1, y1, just times by lambda 1. I can just write that as lambda1 x1. Okay, and this likewise is our lambda2 x2 there. Now in the book, when they come up with that, if you have a look, when they come up with P, they come up with that matrix by saying x1, x2, and they're defining x1 there to be your eigenvector. So they're using a capital there, but in the previous exercise, they've used lowercase, so I've stuck with lowercase. Okay, so this is really a matrix here, and just this and this, and that's here and here. It's a matrix because that vector has two parts to it. Okay, now that's P times by D, and you can see that that's exactly the same as, now this one here, this thing here, so that's AX1, so that's AX1 there, going inside that matrix, and that's AX2 there, and again, that's how we define things in the first place, to find eigenvalues and eigenvectors. Okay, so given that this is the same as this using this, then we can also see that if we applied here A to this thing here to P, so let's just do that one, let's do A times by P there, the matrix A times by the matrix P. Well, when we apply this to this, that's going to give us the same thing as this. Okay, now that's a bit like when we apply transformations to multiple points. If we apply to just one point, we'll end up getting out the matrix A applied to x1. If we apply it to 2 points, we then get the second point in our second column. So this is the same thing essentially. This is equal to A times by P. And so we've shown there that through here to here essentially, and through the multiplication of P and D, that this is giving us our A times by P there. Okay, and if AP is equal to PD, which we've now shown, then all of this follows. So this here is just my little -1 on the end there. So A to the power of n is equal to this thing here. Okay, so this is the really important result which we're going to be using. Now, before we can use that, we need to actually work out our eigenvalues and put them in a diagonal matrix, and we need to work out our eigenvectors and put them into a matrix there for P as well. Okay, so let's have a look at the question. So we're going to take example 13, of course, and let's take this one, and I'll try and do as much of this working out as I can, but obviously there's a lot of working out here, so I might show a little bit of what's in the question here as well. So it says, find the diagonalization of A. So that's what we've got to do to start off with. Now, diagonalization means, of course, that we're looking for our two eigen values in this case. So eigenvalues exist when this is a singular matrix. It's a singular matrix, and sorry, not when that's a singular matrix, but when, let's just write that one out from before, when A times by your x minus, let's just take that back, sorry, minus lambda x, up a little bit here, sorry, minus lambda1 times by, let's just keep it as a lambda I, that's I with the identity matrix, which is 2 by 2, and that applied to your eigenvector is going to give you 0. So that is developed from where we started, say this. Okay, so that's the start point, and this is what we need to use. And of course, that's what we did in the previous exercise before. Okay, so here we need to then subtract lambda from our diagonals essentially. So there's 2, and then we've got 3, and then we've got minus lambda there. We want to take the determinant of this and set that equal to 0. Okay, and so that's going to give us that's good. So this has got to be your singular matrix, and of course, if it's got I'm going back to the previous bit essentially, but if this matrix has got an inverse, then that will make our eigenvector 0, 0, which is kind of boring. So we're going to need to say, well, if this is a singular matrix, then it's got no inverse. And if it's got no inverse, then we need to take the determinant of this matrix here, and then which is this thing here, of course, and then set that equal to 0. That's all explained in the previous one, of course. So in order to do that, we're going to do A times D, so A times D. Okay, and then take away 3 times 2 there. Take away the 3 times 2, and then equal to 0. And so in this case, we've got lambda squared, we've got minus lambda, we've got minus 6 is equal to 0. And so we've got lambda and minus 3 there, and lambda and plus 2 there equal to 0. So that's implying that lambda 1 is equal to 3 and lambda 2 is equal to minus 2. Okay, so we found that. So our diagonal matrix in this case is going to be equal to R3 and minus 2. Now, let me just check to see if they've got them the same way round here. 3 and minus 2, so they've got them the same way round in this case as well. You could have them either way round, of course, but that would just give us a different diagonal matrix. But I've got them the same way round as the book there. Okay, so that's the diagonal matrix, and now we need to make P. So P for this part here is going to require us to have 2 eigenvectors. Now remember that the eigenvectors are going to be putting these things back into this matrix here. So the matrix here, if I put these brackets around, which is essentially this, and then applying them to your eigenvector to get the 0. So let's do that then. So let's put the 3 back into here, and we've got minus 2 and 2 and 3 and minus 3 there. When we apply that, this thing here, to our xy, so particular, let's call that one x1, y1 if you want, because this one is called lambda 1, but we can just call them x and y as well. So let's just call them x and y in this case, just keep it a little simpler. That's going to be equal to 0, 0. That gives us the 2 equations here of minus 2x and plus 2y equals to 0. And it also gives us 3x and minus 3y equals to 0. And obviously they're both going to give us the same 2 equations there, which is that y is equal to x. Okay, so y is equal to x from that. So that's for this one, and if we do the same for this one here as well, we'll get out 3, and obviously 2 and 3 there. And we're getting 2 there as well. And you can see in this case, it's giving us the same equation twice, and that same equation is going to be 3x plus 2y is equal to 0, which is telling us that y is equal to our 2y, sorry, minus 3x divided by 2. So minus 3 over 2x. Okay, so that's our second eigenvector, or is going to give us our second eigenvector. So this simple eigenvector would give us, say, for example, t, if we chose to use a parameter there. And t can be anything essentially, but let's choose 1 and 1, t to be 1 essentially. And likewise, this is going to give us, if we put in x is equal to 1 here, then this is going to give us y is equal to minus 3 over 2. So that's what I'm going to stick with in this case. Now, it could be that we prefer to choose 2 there, because that would give us 2 and minus 3, and then there's no fractions. So let's just see what the book chooses to do. And let's be consistent with that. Yeah, so the book has actually chosen the t, if you like, to be equal to 2, or the x value to be equal to 2. So that's the x2 that you're seeing down here. So let's go with that. So let's double everything there just to make the numbers easier. Okay, so 2 and minus 3. Okay, so there's your two eigenvectors. So that means to say that P is equal to 1, 1, and 2, and minus 3. Okay, good. So now we've sorted out P, we've sorted out D. Now we're asked to find an expression for a to the power of 4. Okay, so let's try and squeeze this in down here. We've got a to the power of 4 then is equal to P, so this 1, 2, 1 minus 3, and then d to the power of 4, which is going to be 3 to the power of 4, so that's 81, and minus 2 to the power of 4, so that's going to be 16 there. Got 0 there and 0 there, and then I'll need to work out what P the minus 1 is, and I can either use my calculator to work that one out, or I can use the formula from the formula booklet as well. So this thing I need to work out. Okay, now conveniently I'm running out of space here, but let's show you how they do this one in the book now. So you can see that they've got the same thing. They've got P as 1, 1, and then 2 minus 3. They've got the D is 3, 0, and 0 minus 2, and they've worked out P to the minus 1. Again, they've used the same formula which we keep using here, which you need to have a lot of practice with, which is 1 over the determinant of P, and then switch around D and A, and then make your B and your C negative. Now, I'm not liking the look of that one, because they've got the fact that, in fact, they've messed that formula up, because that should be minus D there and minus C there. The B and the C remain in the same position. And actually, you can see that they've done it correctly here. So this is minus 2. So they've just made the B position negative, and they've made the C position negative. So you don't need to swap around the B and the C. Don't know why they've done that. That's just a mistake. Okay, so it should be minus B there and minus C there. Okay, so after that, of course, you can now apply a to the power of 4 is equal to your P times d to the 4. There's d to the 4. That's what I was just doing before. And this is your inverse matrix. And it seems to me like they haven't done anything further there. But you can see that, in fact, that would be quite easy now to multiply out. You could multiply these two out and then this one out here. And so the number of calculations, if say n is to the power of 100, now becomes far, far fewer for a program to sort out. Okay, so there we go. I think we've answered all of the questions there. So last part said, find an expression for a to the power of 4, and so it was only the expression which we needed. Okay, so final part here is it's now saying let's return to the transition matrices. So there's a nice investigation which is following this, and I might just do a little bit of this now, but again, the investigation is good here. And again, you could imagine this would be one of the longer questions that you get on your third paper, where you get half an hour per question. So let's have a quick look at what it's saying. Saying return to transition matrices. It says you saw how to find the steady state of a dynamic system by considering high powers of the transition matrices, or by solving the equation Tu equals U. Now we did both of those things in the previous one of the previous exercises. In fact, let's just go back, because that was a really good question. It's important that you have done that one. So that was question 2 from 9H. And so it asks you to work out U in 2 different ways. So it said find U by solving a system of equations. So that was solving Tu equals U by multiplying out a matrix with a vector to get that same vector again, so coming up with 3 simultaneous equations. Part B was saying demonstrate this answer by finding the long-term probability matrix. That is to say, if you apply T n times over and then apply it to U, you should also tend towards U. Okay, so if we could do t to the power of n and n was really large, then we could work out what our steady state probability matrix is, essentially. So what the probabilities would tend towards over time in these Markov chains, essentially. Okay, so let's go back to what they're talking about here again. So here it goes down here. So that's what they're talking about there. So that was 9H question 2. It's a really important one to do. But then it says this section will show you the same results can be obtained using diagonalization. Right, okay, so that's essentially saying, so let's just take this thing here, just to show you what they're talking about here. So they're saying t applied to u gives us u. So if we've already got our steady state vector and we apply t one more time to it, we'll still get the steady state vector. But if you had an initial state vector, let's for example call it u0, and we apply t to that, n times over, and if n is large, then this will tend towards u, the steady state vector, as n tends to infinity. So now we actually have the possibility to work out t to the power of n, and we can tend this to infinity by considering our diagonalization. Okay, so let's look at the investigation. So if we have a look at this one here, now let's just make some sense of this. So they're talking about different neighborhoods and people switching between neighborhoods over years, and they're saying here, this is what's been happening since 2015. And so they said, well, look, you get 12% of all people from neighborhood B move across to neighborhood A each year, and 8% go the other way. And obviously, 88% stay here and 92% stay here. So there's your 92% staying in A. 8% move across to B. This is the initial A. This is where they end up. And from B, 88% stay where they are, so B to B, and from B to A is 12%. Okay, so that's just making a bit of sense of the matrix which they're coming up with here. That's your transition matrix. This is where we start. This is after 1 year. Okay, so this is your transition matrix. So if you remember from before, the transition matrix should tend towards, if it's a regular transition matrix, should tend towards two probabilities there which are the same. So that will give you your long-term probabilities of ending up in each of the sections. Okay, so well, that will give you long-term probabilities rather of A going to A and B going to A in the long term. Okay, so then it shifts on. So let's have a look at 2 to 6 here. Okay, so for 2 it says the population of the neighborhoods are this and this respectively. So there we go. We've got the information in here for A and for B, and after 1 year the population can be expressed like this. Yeah, we understand that from before. And what is the population after 1 year? So that's essentially just doing this calculation, no problem. And the eigenvalues and eigenvectors of T. So what they're leading us to do here now is to change T, like what we had before for A. So what they want us to build up to is T to the power of n is equal to Rp d to the power of n p to the minus 1. So through that process from before, again, we're going to need to create our eigenvalues by taking off lambda lots of the identity matrix again, and then setting the determinant of that equal to 0. And if you solve that, you will get two answers of 1 and 0.8 as your two eigenvalues. Now, I'm not going to do that here, but you should get lambda 1 is equal to 1 and lambda 2 is equal to 0.8. Okay, this will come from a factorization. Of course, that's really 4/5. So one of your brackets will essentially be 5x minus 4, and the other bracket will be x minus 1. Okay, so that's what will come from setting your determinant equal to 0. So once you've found these ones here, you can obviously put those ones in your diagonal matrix, and then of course you go through that process of finding your eigenvectors. And again, that process comes from doing your A minus lambda applied to the identity matrix, applied to x is equal to 0. So you're going to need to now substitute your values into here, and then I know there's a long process, and then you'll find your equations of your lines, your invariant lines, and then you will obviously find your eigenvectors. Okay, long process. Okay, so then let's go back. And so once you've done that, I mean, I think you can see where this is going now. We're applying d to the power of n. So this is the kind of interesting bit here. They're saying, well, look, as n tends to infinity, what happens to this diagonal matrix when we go d to the power of n? And that will affect, of course, what happens to t to the power of n. Now, 1 to the power of n is just going to remain as 1. So d to the power of n will tend towards this matrix 1, 0, 1 to the power of infinity is still 1, and 0.8 to the power of infinity, or to the power of a large value of n, is going to tend towards 0. If you constantly take 80% of the previous value, you will eventually get something extremely small. So this is going to be 0, 0 here. Right, so finally, you can now put this into here. Okay, so we're getting now 3, 1, 2, minus 1, applying to 1, 0, 0, 1. And then if we do that, then we can apply that to this. So if we do that, of course, we're getting just putting the brackets around the first two there. We can put brackets around the first two or the last two, and the first two makes it easier. So this times this is going to give us 3 here. And then this times this gives us 0. And then this times this gives us the 2, adding those two things together, of course. And then this times this gives us 0. Okay, so this is the matrix which we now need to apply to this. So final step then, t to the power of n is going to give us 3, 2, 0, 0 applied to 0.2, 0.2, and 0.4 minus 0.6. And that's this times this, and add them together, is going to give us 0.6. And then this times this also gives us 0.6. And then we've got this times this gives us 0.4. And this times this gives us 0.4 as well. Okay, so t to the power of n gives us this as our transition matrix raised to the power of n. Right, so if you want to work out the long-term populations of the neighborhoods, you'll now need to apply this to this vector here. So that would be your final thing that you would do. Now, in this matrix here, this is saying basically A, B there, right? This is saying what's the probability that if you start in A, that after n transitions, or infinitely many transitions, that you end up in A? Well, it turns out that it's 60% true that you will end up in A if you started in A ultimately. And the same is true about B as well. Okay, and obviously we're getting values here and here which are the same because this is a regular transition matrix and we're only dealing with regular ones in this case. Okay, guys, well, there's some tricky stuff there. That's going to take a lot of practice. Go carefully through that question, I suggest, this one here. Carefully again, if you didn't quite get it the first time round, try and do it yourself as well. These two boxes are critically important. It was important as well that they said essentially that A is diagonalizable if if A can be written, so if we can find the two eigenvalues for A, so that it's got two distinct real eigenvalues. If when you set the determinant of that matrix which we found equal to 0 and it doesn't give you two distinct values, then you don't have a diagonalizable matrix. Now, your questions will have that, but that might be a question that they pick on. So obviously go through these pink boxes with a lot of care. Okay then, guys, so thanks for listening and good luck with the exercises. This is the last exercise on matrices. This is, just have a little look, this is 9J. This gives us 4 questions here, and I really recommend that you do get as much practice with this as possible. Okay, thanks for listening, and hopefully see you for another one later on.